Okay, so in this video I am going to talk about subgroups of a group. We have seen some examples of these already. So, I am going to define these and then we will look at examples and properties. So, a subgroup of a group is simply, I mean I will say it in words first, is simply a subset of a group which has the properties of a group. So, let us fix a group. Let us say G is a group, a subgroup of G. So, let us say a subgroup H of G is a subset of G. So, to begin with it is a subset of G which has the following properties. Which has the following properties. 1, H is closed under the operation of So, this means remember that if A and B are in H, this implies A B is in H. Remember, this is really not always true, because if A and B are in H, they are in G. So, A B is in G, but here we want it to be in H again. So, it is a condition on H. So, it must be closed under a binary operation of G. The identity element must be in H, and 3, if A is in H, then A inverse should be in H. Okay, so, this is a subgroup. So, that is all. So, that is the definition of a subgroup. This the third condition here is saying that if an element is in H, its inverse is also in H. Again remember that inverse is in G, but it need not be in H, we want it to be in H. So, I will only remark here an easy remark: if H is a subgroup of G, then H is also a group under the same operation as So, if you focus your attention only on H, it is actually a group, because it has a binary operation. It is the same as the one of G. It has identity element, it has inverses, but group has another property, right, which is associativity. But remember that associativity comes for free in this case, because associativity holds in G. So, if you get 3 elements A, B, C in G, you can group them in any of the 2 ways to get the same answer. Hence, if 3 elements are given in H, associativity holds automatically for them, because they are elements of G. So, it is also a group. We do not need to check for associativity separately. So, some immediate examples and non examples really. Z is a subgroup of Q under addition. So, this is obvious, right, because under addition Z is Q is a group to begin with, Z is closed under addition, it has 0 and it has inverses. Okay. So, similarly Q is a subgroup of R or C, again under addition. Q star, which is remember non-zero rationals, is a subgroup of R star or C star. These are non-zero reals, these are non-zero complexes, this is under multiplication. I am not checking this in detail, but it is very clear, right. Q star is a subgroup of R star because it is closed under multiplication, it has identity, it has inverses. What about Z star? Is not a subgroup, for example, of Q star. Non-zero integers do not form a subgroup under of Q star under multiplication, because it is closed under multiplication, it has identity, but it does not have inverses. See, note that the reason is the same as the reason that we saw in an earlier video, that Z star is not a group. So, it can't be a subgroup of Q star. Okay. So, some more interesting examples. Let us take the subset of Z consisting of even integers. So, in other words, H is 2n as n varies over z, right. Even integers are divisible by 2. So, they are always multiples of 2. So, you can write them as 2 times n as n varies over z. Is this a subgroup? Is this a subgroup of z? Let us check one by one. What are the properties? Is even integers closed under the binary operation, which is of course, I have not emphasized here because it is clear generally. I am considering z under addition. So, I take z under addition and take h to be the even integers. Are they closed under the addition of integers? Yes. If you sum 2 even integers, it is an even integer, right. Is the identity element in the set h? Yes, because 0, which is the identity element, is an even integer. Similarly, if n is an even integer, its inverse, what is inverse under addition? It is minus. Okay. So, minus of an even integer, it is yes, it is a subgroup, and the reasons I will not write this, but I will just say that 0 is an even integer, sum of even integers is an even integer, negative of an even integer is an even integer. So, even integers form a subgroup. What about odd integers? So, take the subset of odd integers, is it a subgroup? Certainly, it is not a subgroup, because it is neither closed nor does it have an identity element, because you can have sum of 2 odd integers and you get to get an even integer. 3 plus 3 is 6, 3 and 3 is odd, but the sum of 3 and 3 is 6. Similarly, 0 is not there. So, because 0 for example is not odd. So, odd integers do not form a subgroup, but even integers do. What about this set 3n n in z? Earlier we took 2n, which is the even integers, right. That is a group subgroup which saw. What about odd multiples of 3? So, these are all multiples of 3. So, this set is actually minus 6, minus 3, 0, 3, 6, 9, 12 and so on. That is this set. This is also a group. This is a subgroup of Z, because 0 is there, sum of any two things here will be again a multiple of 3. If you take two multiples of 3 and sum them, For example, 3 plus 6 is 9, which is also a multiple of 3, but more generally if you do 3n plus 3m, it will be 3 times n plus m. So, it is closed under addition, and negative of a multiple of 3 is also a multiple of 3. So, it is a subgroup of Z. More generally, A Z, which is by definition all multiples of A, is a subgroup of Z for any A in Z. Okay, so maybe I will write that as a theorem, or let me wait for the theorem, but why is this why is the previous statement true? A Z is a subgroup for any A in Z. It is exactly the same reason as it is for 2 Z and 3 Z. Remember, this is nothing but 3 Z, and the even integers are nothing but 2 Z. So, all multiples of 2. So, this 2 Z is just my notation. More generally, A Z is a collection of all multiples of A. It is a subgroup of Z for every small a, because if you take 0, n as 0, 0 is inside that. So, let me just check by one. So, A Z is closed under addition. Why? Because if you take A n plus A m, this is an multiple of A, this is a multiple of A, you are adding them, you get A times n plus m, which is also a multiple of A. So, that is okay. A Z contains 0, certainly, because 0 is A times 0. Remember, A Z is all multiples of A. So, you can take A n for every n in Z. So, in particular when you take n equal to 0, you get 0. And similarly, A Z is closed, contains inverses. That is because inverse of A n is A times minus n. So, that is also inside A Z. So, A Z is, so these 3 points imply that A Z is a subgroup, okay, Z. Now, the theorem that I want to write and prove is that every subgroup of Z is of the form A Z for some positive integer okay. So, for some integer, not positive, but some non-negative integer A. Okay, so, this is the theorem. So, I am earlier before the theorem I showed that A times Z is a subgroup for every small a, but now I am making the converse statement. I am saying that every subgroup of Z is of the form A Z, this specific kind of a subgroup. This requires a proof, right? These look like specific kinds of subgroups, but why should every subgroup of Z be of that form? So, let us prove this. So, how do I prove this statement? I am going to prove that any subgroup you give me of Z must equal A Z, where A is some non-negative integer. So, let me prove it by first starting with an arbitrary subgroup of Z. Let us say H is a subgroup of Z. So, we are going to first assume that consider the case that H is 0. That is certainly a possibility, right? 0 by itself is a subgroup of Z. If H is just 0, then is it of the form A Z? Yes, it is of the form 0 comma Z. because this is 0 times n, n in z, that means this is just 0. So, remember I am allowed to take any non-negative integer a, I am going to take 0 in this case. If h consists only of the 0 element, it is 0 z, which is of the required form. So, that case is done. So, now, suppose that h is not just the 0 element. So, h contains an integer n, right, which is different from 0. Because h is a subgroup of z, it is not just the single element 0, that means it contains a non-zero integer. Yes. So, it contains a non-zero integer. I claim that in fact, h contains a positive integer. Why is this? Why? Okay, so, I first said that h contains an integer n non-zero. So, let n non-zero be an element of h. I know that there is a non-zero element, because remember I have assumed that h is not 0. H equal to 0 case I have already settled. So, h is not equal to the single element 0. So, it contains an element n of which is different from 0. If n is positive, we are done. We are done in the sense that we are done with this statement. I am trying to prove that it contains a positive integer. So, if n itself is positive, we are done. If n is less than 0, remember n is different from 0. So, n is either strictly more than 0 or strictly less than 0. If n is less than 0, minus n is positive, right. If n is less than 0, minus n is greater than 0. But I claim that since n belongs to h, minus n also belongs to h. Why is this? This is because h is a subgroup. This is where we have used the fact that h is a subgroup. Remember, if you recall the definition of a subgroup, if A belongs to h, A inverse belongs to h, the inverse of A belongs to h. In my example, I am working with z under addition. So, inverses are negatives. If n is in h, so n is in h, minus n is also in h. So, if n is negative, minus n is positive. So, I have justified this statement here that h contains a positive integer n. Now, define or let A be the smallest This is a very important argument, you should pay close attention to this. This comes up a lot in algebra. So, I have first said h contains a positive integer. Now, I am going to take the smallest positive integer contained in h. Remember that h contains perhaps lots of positive integers, but there will always be a smallest positive integer, because any set of positive integers has a smallest element. So, if you take the set of positive integers in h, it will contain a smallest element. So, I take a to be the smallest positive integer in h. So, how do I get a? So, I will start with 1. Is 1 in h? If not, I will go to 2. Is 2 in h? If not, I will go to 3. If 3 is not in h, I will check with 4, otherwise I will check with 5. Because h contains a positive integer, at some point we will reach a number which is in h. The first time we reach that is the smallest positive integer that is in h. So, I will call that a. Then we claim that H must contain only multiples of H, A is my claim, which also proves the theorem. So, why is H equal to A Z? So, now let us say B, so let us say B is a positive integer in H. So, let us say, let me write it like this, let B in H and assume okay. So, let us say B is in H and assume B is positive. So, I am going to consider this case. By the choice of A, what is choice of A? A is the smallest positive integer contained in H. B is some other positive integer contained in H. So, by choice of A, we have B greater than or equal to A. B could be A of course, but it can't be smaller than A. So, now we divide B by A. So, you all know division, what does it mean? So, if I divide B by A, I can write it like this, B equals sum A times sum P plus Q. So, if I divide an integer by another integer, I will have some remainder. What is the properties of this P and Q? P is some Z, element of Z, and Q, the important property is Q is strictly between, sorry, Q is non-negative, but it is strictly less than A. See, remainder is always less than A, correct, because if Q is more than or equal to A, I can further divide. Okay. So, I can keep dividing until the remainder is strictly less than A. So, I have this. Now, this equation will translate to B minus A P equal to Q. Now, let us observe this closely. B is in H, that is by hypothesis. A is of course in H, because A was chosen to be, remember that A was the smallest positive integer contained in H. So, we claim A is in H, B is in H, again using the properties of a subgroup. So, note that A is in H, so minus A P is in H, because H is a subgroup minus A P. What is minus A P? So, actually if you want to do step by step, if A is in H, why is minus A P in H? Minus A P, remember, is P times minus A. I can write it like this. That means, it is minus A plus minus A plus minus A P times. A is in H. So, minus A is in H, that is the property of a subgroup. If minus A is in H, P times you add minus A to itself, that is also in H. So, that is the proof for this. Similarly, B is in H, that is also given. Hence, B minus A P in H. So, A is in H, minus A P is in H, so and B is in H. So, the B plus minus A P is also in H. So, B minus A P is in H, then Q is in H, right, because B minus A P is equal to Q. So, Q is in H. But now, let us see something interesting happens. Q is in H, but Q is strictly less than A. Q is strictly less than A. Can Q be positive now? It cannot be. Q can't be positive, because Q is strictly less than A and A is the smallest positive integer in H, and Q, remember, is the conclusion at this point is Q is in H. So, q can't be in. If q is in H and it is positive and it is less than a, that violates the choice of a. A was chosen to be the smallest positive integer. So, q must be 0. Then if q is 0, the remainder is 0. If q is 0, b is, this is 0. So, b is equal to AP. So, if b is AP, this means that b is inside AZ. See, I have started with an arbitrary element of H which is positive and concluded that it is a multiple of AP, a multiple of A. I do not care what P is, it is just a multiple of A, that is what I am interested in. So, every positive number in H is a multiple of A. What about negative integer? So, if let us say b is a negative integer, if b is in H and b is less than 0, consider minus b, which will be positive. Minus b is in H because b is in H and H is a subgroup. Minus b is in H, and by what we have already shown, which is that every positive integer is a multiple of A, minus b is a multiple of A for some p. But then b is A times minus p. So, b is also a multiple of, in other words, so we have showed that every element of H is a multiple of A. Hence, H is contained in AZ. Remember, AZ is the set of all multiples of A. H, every element of H is a multiple of A. So, H is contained in AZ, but clearly because two reasons. H is a subgroup and A is in H. A is in H because remember A is the smallest positive integer that is in H. So, A is in H, H is a subgroup. So, twice A is in H, thrice A is in H, 100 times A is in H. So, all multiples of positive multiples of A are in H. Because A is in H, minus A is in H, and all positive multiples of minus A are in H. So, entire AZ is contained in H. So, AZ equal to H. Remember, that is what we are trying to prove. So, this completes the proof. This completes the proof of the theorem that we have every subgroup. So, I think the theorem is here. What is the theorem? So, let us see. Every subgroup of Z is of the form AZ for some non-negative integer AZ, for some non-negative integer A in Z. So, this is very strong property of subgroups of Z. So, I want to just make one more remark. As I said, this is an important proof. Okay. So, in this proof, as I said, the proof is very important to understand, and just to emphasize one point, what we have really done is, you take the integers, 0 is here, I am looking at a subgroup of Z. I have taken the smallest positive integer. So, A is the smallest positive integer in Z, in H. So that means there is between 0 and A there is nothing in H. So as you go from 0 to the right, first time you hit H is at A. Okay. So then next time you hit H is 2A. So there is nothing in between A and 2A that can be in H. That is because if there is something in between, by subtracting A you land here. But then we know that there is nothing between 0 and A in H. Similarly, at the next one is 3A. Next one is 4A. So H must be only multiples of. So similarly, between minus A and 0, there can't be anything in H. Because if there was something here in H, its negative will come here. And that will violate the property that A is the smallest positive integer. So in some sense, A must be, H must be just this made up of these multiples of A. Okay, so and nothing in between these multiples can be in H. So this is exactly what we have done. So subgroups of Z are particularly simple in this way. One more remark. Every group has two obvious subgroups. Right? No matter what the group is, it has two obvious subgroups. You can take E is a subgroup of Z. Definitely it's a subgroup of G because it is closed under the binary operation. There's just one element. So if you apply E squared, E cubed, there it's all E. So it is closed under the binary operation. The identity is there. Inverses are there. So it is subgroup. Similarly, this is called a trivial subgroup. Okay, so it is trivial because it has just E. G is also a subgroup. G is a subgroup of G also because it is certainly a group. So and it's closed under the binary operation by definition. It has inverses, it has identity. So it is the full group. So these are not interesting. So typically we are interested in subgroups which are neither the trivial subgroup or the full subgroup.